Thank you for the heads up. Next up, I want to introduce Niall Moroney. He's lead solutions engineer at Q-CTRL. They're doing really interesting work in GPS-denied solutions. His talk is titled Quantum Navigation, Next Generation Capabilities for Maritime and Defense Platforms. So let's welcome Niall.
Hey everyone, it's great to be here at the first conference for combining the maritime industry and also the quantum tech industry. Just wanted to get like a quick show of hands where people think the opportunity for the maritime sector from quantum technology comes from. I heard quite a lot about computing. Who thinks that'll be the first? About communications, ship to shore. And then what about sensing? So a few for sensing. So I guess really my job here is to bring as many people onto that final show of hands as possible. So with quantum advantage, this is often talked about in terms of quantum computing. It's about using the significant computational power of quantum computers to solve problems that would not be possible today. What we showed earlier this year at Q-CTRL has been the first example of commercial quantum advantage. Here, not in the area of quantum computing, but rather in an adjacent area of sensing for GPS-denied navigation. And so that's what I'm going to talk to you about today. For those of you who aren't aware of Q-CTRL, we make infrastructure software, AI-powered infrastructure software to make quantum hardware work better. And we do this in two key verticals. So we actually work in quantum computing. We make software that makes the quantum computers up to 1,000 times better than if you weren't using our methods. And so here we work with people who make quantum computers themselves because they want to be able to showcase the best that their devices can do. And we also work with end users who want to use these devices to solve their real-world problems. In sensing, we use our core capability of this AI-powered infrastructure software to get the best out of the underlying hardware. For sensing, it's slightly different. We here call this software ruggedized quantum sensing. It's about using software to enable the use of quantum sensors in the real world. There's lots of fantastic demonstrations in the lab of the power of these new types of sensors. But when you go from the lab into the real world to try and solve actual problems, you come across a whole ton of failure modes that myself as an experimental physicist isn't used to seeing in the lab. And so what we use is our infrastructure software to ruggedize the sensor, to allow it to work in the real world, to allow us to solve real world problems. And it's always great when your work is broadcast to the world from Times Square. So yeah, this was earlier this year. We had, as I say, the first demonstration of commercial quantum advantage. This is using a quantum technology to perform a real-world problem better than the best comparable classical technology. The application here was navigation. And so I started working in navigation maybe about 10 to 15 years ago. And back in the day, people didn't realize that there was a problem waiting just around the corner. So we're so used to using GPS. GPS is an undeniably fantastic technology. It's available all across the globe. It's basically free. At the point of use, it's free. And it gives you centimeter level precision for positioning. The problem is that it relies on very small signals from space that are very easy to jam or to spoof. And so increasingly, we're seeing news articles like this on the board here from the New York Times a year ago. Because of our reliance on GPS and its vulnerability, it's become a key target for bad actors. And independent studies have been conducted both in the US and the UK, and for both countries individually, the daily cost of a GPS outage is set at over $1 billion US. To clarify, that is per day. This is also for small scale, for low duration GPS outage events. If this was to be a prolonged outage, then we would expect more sectors to be affected, and we would expect this number to go up. So Mike, our CEO, gave a very similar talk a few months ago in London, and when we first had our results that I'll go through shortly. On the day as he was on stage, not too far from here, a GPS denial attack was conducted against a ship that ran aground. So on top of the economic impact I was talking about before, we have just a safety impact. This is people's lives who are at danger here. And again, it's been mentioned before here today, but just this weekend, again, very close to here in Qatar, they've had to close their waters for what appears to be GPS interference. Seems to be the reason behind this. If it's not, what we know is that bad actors across the globe will be seeing the strategic importance of how GPS interference can be used as a weapon. These things are only going to increase in the future. And so I think we can agree that there's a problem here, and what we need is a solution. So we need that solution to be a navigation system that can perform in GPS-denied environments, something that's unjammable. Really, we want something a little bit more than that as well, because there are existing alternatives to GPS for navigation. Previously, we've heard about inertial navigation systems. So these measure the motion of the craft that they're on. So every aircraft, every ship has an INS, inertial navigation system, on board. What this does is it measures the motion of the craft, and it adds it up over time. And there is the issue, is that it adds it up over time. So any small, imperceptible errors at any one stage get added up over time. And so your errors build, and you quite quickly lose knowledge as to where you actually are. There are other alternatives also. Say some people may have seen that UAVs can have cameras added to them, and you can perform what's called visual navigation. We can see in this picture, though, it doesn't work all that well over an ocean where there aren't all that many visual features to reference to. So what we need is an overall solution that works in GPS-denied environments. It works in day or night. You don't need to see the ground. It also works in all weathers. And for some of the defense users as well, we want something that isn't broadcasting your location, so a passive system that's not telling everybody where you are and what you're up to. And so often I think that innovation is best when you take new technology and apply it to old ideas. And so that's exactly what we've done. We've come up with quantum orienteering. So I actually started my career as a military officer in the UK. And quite often I was tasked with running from A to B in the British countryside, almost always in the rain. And to do so, I used 3 key things. So firstly, I had a map in my hand. I used this map to find unique features around me. Then second, I used my eyes to see those features. And third, I used my brain. So my brain was first to make sure that I'm focusing only on the features of interest, and then using that to work out what I want to do next. So that's what we've done. We need unique features. And luckily, the planet Earth has given us 2 different sets of them. So just before, Renia was talking to us about this unique magnetic fingerprint that can be shown. You see that I've got this Q-CTRL headquartered in Sydney, Australia. So I've got, this is the magnetic fingerprint of Australia. Similarly, different rock formations. You can imagine underfoot, if you have a particularly dense set of rock, then gravity is ever so slightly higher. With a sufficiently sensitive gravimeter, something that measures gravity, then you're able to measure these fractional signals. But as I say, these are tiny, tiny signals. And so you need a set of eyes that can see these signals which are invisible. these sets of eyes need to be sensitive enough to see the tiny fluctuations that we're trying to use to navigate on. And then really importantly also, is that the sensor needs to be stable. We need to be able to trust the sensor for long enough to perform navigation, and this is where stability comes in, because we don't have the chance to regularly perform calibrations. So quantum sensors have the unique sensitivity and stability required to be the eyes for this new quantum orienteering. And so we've made one. Rennie before was saying that I think this is a quote in terms of how good of a sensitivity it is that it's crazy good. So yeah, we're using the kind of OPM technology that Rennie spent some time going through before. I just wanted to highlight how low swap this device is. It's just a bit larger than my finger. It uses less than 15 watts of power. We've also tested it in a range of operating environments. So this is a sensor that this is a quantum sensor that has been designed specifically for navigation and specifically for integration into systems as difficult as Class 2 UAVs, and we have done this. So we've made the eyes. We've also packaged this into a product that is ready today, is commercially available today to test on your platforms and your missions to show you the benefits of quantum orienteering. And we give each of the three aspects that are required for this technology. So first of all is the map. This gives the unique fingerprint that you will use to navigate from. Here we just use publicly available maps that we've shown to be completely sufficient for this purpose. Next is the sensor itself. This is what we use to measure the tiny magnetic fluctuations that we use to navigate from. And third comes the Q-CTRL's key competency of infrastructure software. So we first have proprietary denoising algorithms, which means that our magnetometers are really good. They measure everything. They measure all the small bits of magnetic noise that are available as soon as you put this system on board a ship or an aircraft. And so the first thing that we do is we take that noise away, so we're only looking at the features that we want to navigate from. And then second, we have, again, our own AI-powered algorithms for sensor fusion. This is where we take the information from our magnetic system and integrate it with the onboard inertial navigation system to keep it true. And this is a field-tested system. So we've performed over 100 hours. This is counting as well, is that we've got lots of ongoing trials. Currently over 100 hours of airtime with this. And this isn't just some experiment happening in the sky. We put it into the aircraft, turn it on, and it operates by itself without intervention for these 100 hours. We've had it working from ground to 19,000 feet. The height there is limited by the ceiling of the aircraft. We would be able to continue to navigate above this. Also, is that for certain applications, it needs to be able to work in quite a dynamic environment. So the flight that I brought over yesterday was quite gentle. We've tested it with the kind of maneuvers that are necessary for certain defense applications, but that we as commercial passengers would find quite uncomfortable. And there are other aspects as well that we really wanted to test our denoising algorithm to make sure that it works in the real world. Some magnetic navigation doesn't work particularly well either nearby electrical storms or when the autopilot is engaged, because that leads to interference that would negatively impact the results. And so we tested it with both of those, and it continued to work. The key take home is that this works. And we outperformed the inertial navigation system. We outperformed the best classical alternative by a factor of 100 throughout this flight. This is commercial quantum advantage. You can see here how this looks. So there are three different traces on the map here, and this is in white we have the ground truth. This is the track that the pilot actually took on the day. So here we used actual GPS information because the pilots really don't like it if you ask them to turn GPS off properly. With the purple track is almost perfectly overlaid with this white, with the ground truth. This is our navigation solution. This is the information that we will be giving to that pilot if GPS was denied. It can be difficult to see the difference between that and the ground truth just because of how accurate our system is. And then finally is the unaided inertial navigation system. This is what if our solution wasn't integrated into that aircraft and the pilot suffered an actual GPS outage, this is what he would have to rely on. And we can see that it's drifted very significantly over this time. And so I don't want you to just take my word for how impactful this is as a technology. So I've included a quote from one of our key partners in commercial aviation, where they're saying that this is going to be a big game changer in the future. So for some of the experts in the room, I just wanted to go into a little bit more detail about the results that we got from this trial. The first thing I wanted to highlight is just how much better we were. So at the end of the flight, first I'll say is that, so in black we have the solution from the inertial navigation system, and in purple is where we tell the pilot where they are. And so what we see from the end of the flight is that we've got an almost 70 times improvement on the positioning accuracy that we're giving to the crew. This continues, if not, it's better on average. So on average, for the duration of this flight, we were over 110 times more accurate than the best alternative system. The other thing I just wanted to highlight here as well is that the INS, the black line, is always getting worse with time. We can see that as time progresses, it gets more and more inaccurate. This isn't the case for our solution. We can see that Q-CTRL's navigation system gives a bounded solution. It doesn't get progressively worse over time. So the reason for this is because every time we fly over a specific magnetic feature, some unique feature in space, we reset ourselves. And then, and so this always ensures that we don't have this error which grows over time. And we're working quite aggressively to get this integrated into commercial aviation. So Airbus are actually some of our investors, the venture capital wing at least, and we're working very closely with the main co to integrate this into airliners at pace. We're very keen to see what benefits this can bring to the maritime domain also. And so if there is any interest in the room, please do reach out to me, as we're very keen to understand what are the benefits that we can bring to this specific domain. And so, in terms of the maritime domain, I think a few of you may be thinking, well, we're at a Maritime for Quantum event, and Niall, you've just spent 10 minutes talking about airborne trials. And so I also just wanted to highlight that Ironstone Opal that is available today is based on our magnetic system. And that is, we've been looking a lot for aviation. We've done a lot of tests in aviation for that system. We are keen on doing the tests for the maritime domain, but we have built a specific variant of Ironstone Opal that is suited particularly well to the maritime domain. And so every technology has its pros and its cons. One of the potential issues with our magnetic system, with our current system that we've developed, is that seawater can interfere with the magnetic signals that you're using to navigate from. And so we think that our MagNav system won't work great in certain maritime environments. Thinking here, if you're just on the sea surface where you're getting all of these magnetic interference effects. So here we're looking at the signal that we get from gravitational anomalies. What we've done in this is that we sacrifice in order to not be susceptible to the magnetic interference, we've sacrificed in the complexity of the system. And so our gravitational sensor is a little bit less mature. And so we're now working to get this on board ships and to actually demonstrate improvements in overall navigation. And we have done this, so we've de-risked most of the elements associated with gravitational navigation. With this, we've had a week-long trial of our sensor on board an Australian naval ship. And so again, this was not a science experiment. This was something where we put the sensor on board a ship, we turned it on, we let it go, we then weren't allowed on board. We weren't allowed to remote desktop in to make sure it was still working. We just had to trust that it was working. A week later, we came back and it had been capturing data that whole time. And I just wanted to use some of we did some tests when we were on board to check the software ruggedization capability that I was talking about before. So oftentimes with quantum sensing, what you're looking to do is identify a wiggly line. This is as detailed as I'm going to get. And you can see at the bottom, this is us correctly measuring what we want to measure. We can see this wiggly line. We can measure gravity. We will soon be able to navigate. Just above is what happens when we turn our methods off, when we turn our software ruggedization off. All of the noise from being on the platform, this may be the vibrations, for example, it leaks into the system, and it means that you lose the signal. So this is just a demonstration of how our core capability in AI-powered infrastructure software is what enables quantum sensing and is what enables resilient navigation in GPS-denied environments. Now, as I say, this is something that we tested on board. We've done a lot of the de-risking. We've tested this on board ships. This is an image from just last week. We're working very hard to demonstrate a navigation capability using this sensing system. We're just in the process of analyzing some initially promising results, but please do keep in touch. Look at our LinkedIn when we'll be releasing information over the next few weeks or months. And with this work, we've got a lot of interest across the globe. And in particular, we recently won not one, but 2 projects in the US from DARPA to the total of just shy of $25 million US. These are dual programs for taking both our magnetic and our gravitational systems, further miniaturizing them and further ruggedizing them so that they can work on the most challenging platforms to do their most challenging missions. Again, we look forward to giving you more updates as we get some results. So I've left contact details on the slide. I'll also be around for the rest of this event. Please do reach out if this is something that you'd be interested in talking to further.